We will start after 2 minutes. Okay.
Good afternoon,
Good
everyone.
afternoon, everyone.
So,
So,
welcome to the course
welcome to the
Fundamental
course
of
Fundamental of
Nano and Quantum
Nano and
Photonics. So,
Quantum
this
Photonics. So,
is
this is
week 7 of
week
the
7 of this course, and
let's start
let's start
course.
today's course.
Okay, so
Okay,
in the
so
last
in the
6 weeks
last
of this
6 weeks
course,
of this
we
course,
introduced
we
the basic
introduced the basic
material
material
properties
properties
like plasma
like plasmon
and the
resonances
behavior
and the
of
behavior of
EM,
EM,
electromagnetic waves,
electromagnetic
periodic
waves in periodic
structures.
structures.
In the previous
In the
week,
previous week,
we discussed
we
about
discussed
the
about the
materials and
materials and
metasurfaces.
metasurfaces.
So today,
So today,
so today we will
so today
focus
we
on
will
an
focus on
important
an
class of
important class of
materials
materials,
known as tunable
non-as
and
tunable and
active
active
materials or
materials or
metasurfaces.
metasurfaces.
So,
So
why do we need
why do we need
tunability?
tunability?
So,
So
we
so
talk
we
about
talk about
negative index
negative
materials.
index materials.
So,
So
so far we
so
have
far
seen
we
that
have seen that
negative index
negative index
materials work
materials
at
work
RF
at RF
frequencies, and
frequencies,
the
and
negative
the negative
index
index
arises from the
arises from the
overlap of
overlap of
electric and magnetic
electric and magnetic
resonances,
resonances,
which are
which
defined
are
by
defined by
structural
structural
parameters such
parameters
as
such as
the
the
distance and the
distance
gap
and the
between
gap between
rings in split
rings
ring
in split
resonators.
ring resonators. So that
Make
we can make
like
like
this type of
this type of
so we
structures,
can
so we
control
can control
this gap,
this gap,
or if we
or
are
if
making
we are making
such type of
such
ring.
type of rings,
So then this
so then this gap,
so these
so
gaps
these
define,
gaps define,
or if I'm
or
taking
if I'm
two
taking
rings,
two rings,
like one structure
Like
and
one
this,
structure
one
and
structure
this,
and
one
this. So
structure and this. So
I can change
I can change
between this
between
distance.
this distance.
So these are
So
the
these are
structural
the
parameters
structural
that we can
parameters that we
change,
can
and
change,
on the
and
basis
on
of
the
that
basis of that
we can
we
go up
can
to the
go
limit
up
of
to the
negative
limit of
index.
negative index.
So when these
So when
structures
these structures
so when these structures
are
are large,
large,
fabricated on
fabricated on
PCBs,
PCBs,
the resonance
the
lies
resonance
in the
lies in the
gigahertz range.
gigahertz range.
So
So
and if we scale
and if we
them
scale
down,
them down, the
the
resonance frequency
so
increases. So
basically
basically,
we want to
we
shift
want
our
to shift
resonance
our
towards the
resonance
IR
towards the
region,
IR
visible
region,
region.
visible
So for
region.
that
So
we
for
have
that,
to
we have to
optimize our
optimize
structure
our
such
structure such that
that their resonant
their
frequencies
resonant frequencies
increases.
increases.
And for that
And
we
for
have
that, we
to
have to
scale down our
scale down our
structures. So
structures.
suppose
So
if
suppose
in gigahertz
if in
our structures
gigahertz
are
our
in
structures are in
micrometer range or
micrometer range
millimeter
or
range,
millimeter range,
then
so
we have to
then we have to come down into
nanometers range.
nanometers range.
For
For
applications,
applications,
however, it is not
however, it is
sufficient
not
to have a
sufficient to
fixed
have a
resonance
fixed
at
resonance
certain
at
frequencies,
certain
say
frequencies, say
10.5 gigahertz.
10.5
Ideally,
gigahertz. Ideally,
we want
we
post
want post
fabrication
fabrication
tunability.
tunability,
That is
that is
the ability
the
to shift
ability to
the
shift
resonance
the resonance
frequency
frequency
after
after
fabrication. So,
fabrication.
for
So,
example,
for
I want to
example,
move
I
from
want to move from
10.1 to
10.1 to
10.5
10.5
gigahertz, so such
gigahertz,
that
so
we can.
such that we can.
So,
So,
then how can we
then how can
understand
we
the tunable
understand the
split ring
tunable split
resonator?
ring
The structure is
resonator?
the
The
same
structure the
that I
same that I
told in the previous
told in the
slide, made in the
I
previous
made in the
slide.
previous slide.
Okay, so a
Okay,
split
so a
ring
split
resonator
ring
behaves
resonator
like
behaves like an
LC circuit,
LC
and
circuit,
to change
and
its
to change
resonance
its resonant
frequency,
frequency,
we have to
we
tune
have to
either
tune
the
either the
inductance or
inductance or
capacitance.
capacitance.
So capacitance
So
can be
capacitance
controlled
can
by
be
this
controlled
gap,
by this gap,
and the
and
size
the size
of this
of
material
this
will define
material
the
will define
inductance.
the inductance.
So
So
we can think
we can
about
think
one
about
practical
one
approach
practical
is to
approach is
connect a
to connect a
varactor diode,
varactor diode,
that is
that is
a reverse
a
biased
reverse
PN
biased
junction
PN
that
junction
acts as a
that act
voltage
as a
control
voltage
capacitor
control capacitor
across the
across
resonator.
the resonator.
So if we
So if
apply
we
the
apply
voltage,
the voltage,
so in general
so
what
in
we
general,
think
what we
when
think
there is an
when there is an
gain medium, so
gain
when we
medium, so
apply
when we are
voltage,
applying voltage,
depletion
the
region will
depletion region
changes.
which changes.
So if
So
depletion
if
width
depletion width
changes, the
changes,
capacitance
the
changes.
capacitance changes.
And with
And with
change in
change
capacitance,
in
we know that
capacitance, so we know
omega
that omega
naught is equal to
naught
1
is equal
upon
to
root
1 upon
LC.
root LC.
So if that
So if
capacitance
that
will change,
capacitance will change, this
resonance frequency
resonance
will
frequency will change.
okay.
Okay.
So
So
what is the
what is
key
the
point here?
key point here?
Just like we are
Just
applying
like we are applying
voltage,
the
the
voltage,
depletion
the
region is
depletion region
changing,
is
capacitance
changing,
changes,
capacitance
resonance
changes,
frequency
resonant
changes.
frequency changing.
Similar in case
Similar,
of
in
tunable
case of
splitting
tunable
resonator,
splitting
what we can
resonator,
do?
what we can do,
We can increase or
we can
decrease
increase
this
or
gap
decrease this
such that
gaps
we can
such
change
that
our
we can
resonance
change our
frequency.
resonant frequency.
So in
So in
experiments,
experiments,
this approach is
this
widely
approach is
used in
widely
RF
used in
frequency
RF
and can be
frequency and can
easily
be easily
implemented in
implemented in
PCBs.
PCBs.
What are the
What are
challenges
the
in higher
challenges at higher
frequencies?
frequencies?
So,
So,
so there was one
there was
example
one
also
example also
regarding a
regarding
tunable
a tunable
split ring
split
resonator.
ring
So
resonator. So,
a tunable
a
notch
tunable
filter
notch filter
was
was
demonstrated
demonstrated
where the resonance
where the
frequency
resonant
shifts
frequency
from
shifts from
2.5 gigahertz
2.5
to 30
gigahertz to about
gigahertz
3
as the
gigahertz,
applied
and the
voltage
applied
varies
voltage
from
varies
0
from
to 30
0
volt.
to 30 volt. Okay.
So now
So
we will
now
talk
we will
about the
talk about
challenges
the
at higher
challenges at
frequencies.
higher frequencies.
So when we
So
move
when
from
we
the
move from the
gigahertz or
gigahertz or
terahertz
terahertz
to
to
optical or near
optical or near
higher
IR
frequencies,
frequencies,
there are
there are
certain things that
certain things
becomes
that
more
becomes more
challenging because
challenging because
metals no
metals
longer
no
behave as
longer behave
perfect
as perfect
conductors,
conductors,
and
and
so we
so
have to
we
scale
have to
down over
scale
the
down over
structure
the
for
structure for
micrometer,
micrometer, mm,
centimeter range to
centimeter
the
range to the
nano
nano
dimension. So that
dimensions.
is
So that is
these dimensions
these
are
dimensions
much
are
smaller
much smaller
and
and it's
difficult to fabricate.
difficult to fabricate.
So for
So
that,
for that,
we need
we need
alternative materials
alternative materials
and
and
mechanisms are required.
mechanisms are required.
So then,
So
what are
then,
the
what are the
other
other
tuning
tuning
mechanisms?
mechanisms?
So the first
So
is
the
phase
first is
change
phase
materials,
change materials,
which we say
which
PCM.
we say PCM.
So there are
So
certain
there are certain
that
materials
undergo
that
a
undergo a
phase
reversible
transition
phase transition
between crystalline
between
and
crystalline
amorphous
and
state when
amorphous
heated
state
or
when
cooled.
heated or cooled.
So, for
So,
example,
for
we
example,
have a
we have
vanadium
a
dioxide
vanadium dioxide
whose phase
whose
transition
phase
occurs
transition
at 70
occurs at
degrees
70
Celsius.
degrees
So,
Celsius.
suppose if
So,
I
suppose
have
if
a
I
structure
have a
made on the
structure made
vanadium
on the
oxide
vanadium
and
oxide and
I am heating
I
it
am heating
near
it
70
near
degrees
70
Celsius,
degrees Celsius,
that will
that
change
will change
the refractive
the
index
refractive
and
index and
there will be a
there
phase
will be a
transition
phase transition from between crystalline and amorphous state.
The another
The
example is
another
GST,
example is
that is
GST, that is germanium,
palladium
antimony, thallium
glasses.
glasses.
So,
So
what happens
what
when
happens
the phase
when the
transition
phase transition
occurs?
occurs?
So, phase
So phase
transition led
transitions
to
led to
significant changes
significant
in the
changes in
refractive index
refractive
up
index up
from
to like from
1 to 2, that is
1 to 2,
delta
that is
n equals
delta n
to
is equals to
delta n,
delta
the
n.
range of
The
delta n
range of delta
varies
n
from 1 to
varies
2.
from 1 to 2.
So, what are the
So what are the
advantages of these
advantages of these
materials?
materials?
So, the
So
advantage is
the
there is
advantage is there
large
is large
modulation depth.
modulation depth. So
Delta n
delta
is equal to
n
1
is
to is
equals to
very
1 to
high.
is very high range. So
We we can change the
we can change
refractive
the refractive
index
index
up to the
up to the
very large
very
range.
large range.
And what is the
And what is
limitation
the
of this?
limitation of this?
So the
So the
changing in
changing in
from
phase
between
from
crystalline
between
and amorphous
crystalline
and
amorphous or amorphous
crystalline,
and crystalline,
it
it
takes
takes
it takes place
it
in
takes place in
like very
like
slow. That
very
is the
slow. That
switching
is the
speed
switching speed
from crystalline
from
to amorphous
crystalline
or
to
vice
amorphous
versa
or
is
vice versa
relatively
is
slow. That
relatively
is
slow. That is
it is of the
it
order
is
of
of the order of
so
milliseconds.
this is the
So
main
this is the
limitation
main limitation
of these phase
of
change
these phase
materials
change materials,
because in
because in
applications we
applications
want
we
the
want the
devices we
devices
want such
we want
materials
such materials
whose switching
whose
speed
switching
must be
speeds
high.
must be high.
Okay,
Okay,
so this is not
so
in
this is not in
case of these
case of
materials.
these materials.
The next
The next
mechanism is liquid
mechanism is
crystals.
liquid crystals.
So liquid
So liquid
crystals behave
crystals
like
behave
liquids
like liquids
but have
but have
molecular
molecular
ordering like
ordering like
crystals.
crystals.
So their
So their
orientation
orientation we can
can be
can
controlled
be
by
controlled
applying
by
the
applying
electric
the
field or
electric field
temperature.
or
So the
temperature.
process
So
will
the
be same
process
that
will
the
be same that
refractive
the
index will
refractive
change by
index will
applying
change by
electric
applying
field or by
electric field or by
voltage or by
voltage or by
change in
change
temperature.
in temperature.
So we use
So we use
liquid
liquid
crystals in
crystals in
LCD displays,
LCD displays,
and when
and when
we will use
we will use
these
these
liquid
liquid
crystals
crystals
with our
with our
metamaterials.
metamaterials.
So liquid
So
crystals
liquid
can shift
crystals can shift
resonances
resonances
significantly.
significantly.
So
So
the limitation
the
of this is
limitation of
also the
this is
response
also the
time is slow.
response time is
That
slow.
is of the order
That
of
is of
10
the
to
order of
hundreds
10
of
to
milliseconds.
hundreds of milliseconds.
Then the
Then
next
the next
tunable mechanism
tunable
is
mechanism is
mechanical
mechanical
actuation.
actuation.
So what does this
So
mean?
what
So
does this
in
mean?
this
So
case,
in this
we
case,
will
we will
fabricate our
fabricate our
resonators on the
resonators on
elastic
the
substrate. That
elastic
is,
substrate. That
we
is,
can stretch
we can
it,
stretch it,
we can
so we
expand
can
it. It's a
expand it. It's a
flexible substrate.
flexible
That
substrate.
is, it
That
we
is,
can twist
we
it,
can twist it,
we can fold
we
it.
can fold it.
For example,
For example,
PDMS,
PDMS,
or there are
or
many
there are
examples.
many
There are
examples. There
Teflon
are
sheets
Teflon
which are
sheets
also
which are
flexible.
also flexible.
So,
So
if we will
if we will
stretch or
stretch
compress
or
the
compress the
substrate,
substrate,
the gaps.
the gaps.
So
So
suppose we have
suppose we have
material.
this material.
Okay, now
Okay,
this is
now
gap
this is
G.
gap G.
Now,
Now,
if I will stretch
if I will
the
stretch
material,
the material,
what will happen?
what will happen?
This gap will
This
start.
gap will
This gap
start.
will
This
start
gap will
changing,
start changing,
and
and
it will
it
change
will change
my
my
resonant frequency.
resonant
So
frequency. So
stretching
stretching shift resonance.
stretching
Stretching
shift my
will shift
resonance
my resonance peaks
and can even change
and can even
focal
change focal
length
length in metasurface based lenses.
what are the
So what are
limitations
the
of this?
limitation of this?
So first
So
of all,
first of all, it's
difficult to
difficult to
fabricate
fabricate
metasurfaces on
metasurfaces on the
flexible
flexible
substrates,
substrates, and it's
mechanically cumbersome,
mechanically cumbersome
limited
and limited
long-term
long-term
robustness.
robustness.
But the switching
But the
speed is
switching
fast.
speed is
So just we
fast
have to
because just
stretch
we have to stretch it and
it.
we can measure it.
The next is
The next is
carrier injection.
carrier injection.
So
So
if we are
if
doping,
we are doping,
if we are
if we are
injecting
injecting
carriers,
carriers,
that will change
that
the
will change
refractive
the
index of
refractive index of
semiconductors.
semiconductors.
And what
And
are the
what are the
methods for
methods
this?
for
First
this?
is
First
optical
is optical
excitation.
excitation.
What is optical
What is optical
excitation? A
excitation?
short
A
laser
short
pulse
laser pulse
will come
will
and
come
it
and
will
it
generate
will
the
generate
electron
the
hole
electron
pairs,
hole pairs,
and this will
and this
cause
will
a
cause a
transient index
transient
changes
index
lasting
changes
for
lasting for
picoseconds.
picoseconds.
So,
So,
and the next
and
is
the next is
electrical
electrical
injection.
injection.
How can we
How
do this?
can we do this?
We will
That we uh,
will apply the
will
voltage
apply
that
the
is applying
voltage,
the
that is
bias.
applying a bias.
Will
It
introduce
will introduce
carriers,
carriers,
just similar to the
just
MOSFET.
similar to the MOSFET operation.
And this is
And
a
this
very
is a
fast
very fast
technique that is the
technique,
order
that
of
is the order of
picoseconds to
picoseconds to
nanosecond, but
nanosecond,
requires
but requires
integration with
integration with
semiconductor process.
semiconductor process.
So there are
So there are
some
some
advantages and
advantages and
disadvantages.
disadvantages.
Some are easy to
Some are easy
fabricate,
to fabricate,
but
but
the limitation
the
is
limitation
the
is in with
switching
the
speed.
switching speed.
And
And
in this case
in this
also,
case also,
integration
integration
with
with
semiconductor processing
semiconductor
becomes hard,
processing
but
becomes
switching
hard, but
speed
the
is
switching
fast, that
speed
is
is fast, that
picoseconds
is
per
picoseconds
nanosecond.
to nanosecond.
So what are the
So what are the
applications
applications
where we can use
where we
these
can use
tunability
these
mechanisms
tunability
like phase
mechanism
change
like phase change
materials or
materials or
carrier injection
carrier injection
or mechanical
or
actuation?
mechanical
So we
actuation?
can
So we can use
the liquid
the
crystals.
liquid
We use
crystals. We can
these
use these in
like beam
like
steering.
beam steering.
For example,
For
in lidar
example, in
or
lidar
AR
or
display, we
AR
are
display,
generally
we are
using it
generally
also.
using it also.
And where
And
we
where
want the
we
tunable
want the
filters,
tunable filters, we
tune
want
our
to
reflective
tune our resonant
frequencies
frequencies
so that we can
so that we
filter it
can
out.
filter it out. So
Tunable filters
tunable
and
filters
lenses
and
with variable
lenses with
focus
variable
and
focus
special
and special
SLMs, that is the
SLMs, that
special
is the
light
special
modulators.
light modulators.
So there
So
also we
there
use
also we
these
use
ITO
these
based
ITO based
metasurfaces.
metasurfaces.
So these are
So these are
so what is the
so
benefit
what
of
is the
ITO?
benefit of ITO?
So the benefit
So
of
the
ITO
benefit of ITO is
it is a
it is a
conductor.
conductor.
So it's a
So it's a
transparent
transparent
conducting material.
conducting material in visible region.
So if we want
So if we want to deal with
if we want to
if we want to deal
uh,
with
some substances
some substances that are dielectrics
in the visible
in the
region,
visible
we
region,
can
but
coat
we can
ITO so
coat
that
ITO so that it can easily electrons
can conduct
can conduct
can
can
freely move
freely
on the
move
surface
on the
and remain
surface, and it
transparent
is
also.
transparent also.
So what are the
So
figure
what are the figure of merit for tunable metasurfaces?
so
So
that change
that change. So
when we talk
when
about
we talk
the
about the
tunability
tunability
performance, what
performance,
are the
so what are
key
the
performance
key
metrics
performances
and
metrics
modulation
and
strength?
modulation strength?
Modulation strength, that
Modulation
is
strength,
how
that is
much the
how
optical
much the
property
optical property
changes,
changes,
reflection,
reflection,
transmission,
transmission,
absorption, reflective
absorption,
index,
reflective index,
then
then
modulation
modulation
how the
speed,
fast
how
the
the
tuning
fast the
occurs.
tuning
That is we
occurs.
saw
That
that
is, we saw that
um,
uh,
phase change
with the
material
phase
that
change
is of the
materials,
order
that
of
is of the order of
millisecond. Similarly,
millisecond.
liquid crystal
Similarly, in liquid
also
crystal
the
also,
switching
the
speed was
switching speed
millisecond.
was millisecond.
So we can
So
no,
we can no,
can't
we
use
can't
for the
use
fast
for the fast
communication,
communication,
and
and
so there are
so
other
there are
mechanical
other
actuation.
mechanical
The time
actuation. The
switching speed
time
has
switching speed
reduced
has
there,
reduced there,
and also
and also
when we are dealing
when
with
we are
the
dealing with the
carrier injection,
carrier
also there
injections,
is a
also there is a
nanoseconds.
nanoseconds and picoseconds.
So
So
and
we and
energy consumption,
energy
that is how much
consumption, that is
energy is
how much
required to
energy is
switch
required to
states.
switch
That
states.
that's an
That's
important
an important
part that
part, that
like
like
we don't want
we don't
more
want
energy
more
consumption.
energy consumption.
Otherwise, the
Otherwise,
cost will
the
be high.
cost
So we
will be
want
high. So
also
we
the
want
cost
also the
effective
cost effective
and wavelength
and
of
wavelength
operations.
of
It
operation.
depends
So
on
it depends on
so that depends
so
on
that
whether we are
depends on
working
whether
in
we
the
are
visible
working in the
region or
visible
higher
region
region.
or higher region or
Depending
terrain.
upon that,
Depending upon that,
the
depending upon
wavelength,
that, the
like
wavelength,
we will
like
optimize
we
our
will optimize
structures
our
according to
structures
the region.
according to the region of our interest.
Okay,
Okay,
so we can
so
say
I
that
can say
uh,
that like
tunable
tunable
metamaterials
metamaterials
are very
are
essential
very
for
essential for
practical
practical
applications
applications
that require a
that
dynamic
require a
control.
dynamic control.
And
And
so we saw
so
that
we saw that a different
so we saw
so we
the
saw
different
the
tuning
different tuning
mechanisms exist,
mechanisms exist,
each with
each with
the trade-offs
the
in
trade-offs
modulation
in
depth,
modulation depth,
modulation speed,
modulation
and energy.
speed, and energy
So
efficiency.
how are we?
So
How can we say
how
that
can
there
we
is a
say that
trade-off
there's a
between
trade-off between
modulation depth and
modulation depth
modulation
and
speed? So we
modulation
saw
speed? So we
that
saw that
in phase change
in phase change
materials,
materials,
there is the
there
change
is
in
the
reflective
change in
index,
refractive index,
that
that
is
is
equal
del
to
10
1
is
to 2.
equals to 1
This
to
is a
2.
very
This
high
is a
change,
very
but
high
the
change, but this
modulation speed
modulation speed
was of the order
was
of
of the order of
milliseconds.
milliseconds. So
There's a
there's a this
trade-off
is a
between the
trade-off between
modulation
the
depth and
modulation
modulation
depth and modulation
speed.
speed.
So we can decide
So we can
according
decide
to the
according to our
application.
application.
So current
So
active
current active
research
research
explores like
explores
phase change
like phase
materials,
change
liquid
materials,
crystals,
liquid crystals,
semiconductors, 2D
semiconductors, and
materials,
2D
including
materials,
graphene.
including graphene.
So the
So
ultimate
the
goal is
ultimate
to
goal is
achieve
to
high
achieve
modulation
high
depth
modulation depth
plus high
plus
speed
high
plus
speed
low energy
plus low
consumption,
energy
and
consumption,
it
and
should be the
it should be the
compact and
compact and
integrable form.
integrable form.
Okay.
Okay.
So
So
so there
so
are
there are
there are
so
active
there are
and
active and
passive
passive
materials.
materials.
So passive
So
devices.
passive devices.
So we have
So we have
active
active
and passive.
and passive.
So in the
So in
passive
the
thing,
passive thing,
energy is
energy
absorbed.
absorbed,
It's
is
decaying.
decaying.
No addition.
No
No
addition of
addition of energy there.
energy is there.
Okay.
Okay.
So the next is
So the next
active
is
device,
active
which
device,
has
which has
like materials
like
have some
materials have
optical
some
gain.
optical gain.
Okay.
Okay.
So what does
So
it mean
what does it
optical
mean
gain? That
optical
is
gain?
they can
That is they can
amplify the signal.
amplify the signal.
For
For
example,
example,
lasers.
lasers.
Okay.
Okay.
So
So so
nowadays
nowadays,
earlier
so earlier we have
we Fabry cavities
fabric
and we are
cavities and we are
performing
performing the
like we
like
have
we have
electronic components
electronic
like
components like
transistors,
transistors,
so that
so that
we can have
we can have the we
very
have a
large
very large
cavities,
cavities,
large size
large
cavities,
size
and we
cavities,
were
and we were
like we had
like we
lasers.
had lasers.
But now we want
But now we want all these chips,
all the
all
laser
the laser
functionality on a
functionality
single
on
chip.
a
So what
single
is
chip.
the
So what is the
motivation for
motivation for
miniaturizing lasers.
miniaturizing lasers.
There was a
So there
mismatch
was a
between
mismatch between
electronic components,
electronic components,
tiny
tiny
transistors, and
transistors, and
so first of all,
so first of all,
let's
let's
understand
understand
that how
that
the
how the
absorption
absorption
or
or
spontaneous emission
spontaneous
and
emission and
stimulated emission
stimulated emission
takes part in,
takes part in,
like how does it
like
help
how
in
does it
lazy.
help in lazy.
So
Okay,
so we have
so we have a
two level
two
system.
level system.
So
So
there is
there is
ground state
ground state,
that is with
that is with
energy E1
energy E1
and
and
population
population N1.
N. Then other
And
is
then other is
excited state,
excited state,
which is
which
energy
is energy E2
and population.
and population N2.
So at
So
thermal
at thermal equilibrium,
sorry.
sorry,
So at thermal
so at thermal equilibrium,
N2 by
N2 by N1
is equals to
is equals to
exponential
exponential
minus
minus
E2
E2
minus
minus
E1
E1
by K.
by KT.
So
So
in general,
in general,
excitation state is
excitation
always
state is always
less
less
populated.
populated.
So
So
there were three
there were
cases.
three
One is
cases. One
absorption.
is absorption.
Photon will come,
Photon will come,
electron will excite
electron will excite into the
ground state.
ground state.
There is a hole.
There is a hole behind it.
This is first
This
case
is first case
absorption.
absorption. Okay.
Second case is
Second case is
spontaneous emission.
spontaneous emission.
So one photon
So one
will come
photon will come
from the excited
from the
state to
excited state to
the
the
ground state,
ground state,
and then it
and then it will
leave one
leave
photon.
one photon.
That is the second
That is
case.
the
That is
second case. That is the
spontaneous emission.
spontaneous emission.
In the third
In the
case,
third cases,
so there are
so there are
so the, these
so
are
these are
there are some
there are
Einstein
some
coefficient
Einstein
on the
coefficient
basis
on
of
the
which we
basis of which
define
we define
absorption,
absorption,
spontaneous emission,
spontaneous emission rate,
stimulated
and
emission.
stimulated emission.
So the
So
absorption
the
coefficient
absorption
is given
coefficient is
by
given by
A
A,
sorry
sorry,
B12
B12
and 1
and 1
rho V.
rho B.
What is
What
N1?
is
N1 is
N1?
the
N1 is the
population in the ground
population in
state.
the ground state.
So we can
So we
understand
can
that
understand that
how we can
how
define
we
the
can
absorption.
define the
So
absorption. So
if there will
if
be
there will be
more number of
more number of
electrons in the ground
electrons in the
state, then
ground
only
state,
the
then
rate of
only the
absorption
rate of
will be higher.
absorption will be higher.
And that is
So
defined
that
by
is
the
defined by
N1
the
and
N1 and the
density of.
density of states.
Similarly, spontaneous
Similarly,
emission will be
spontaneous emission
defined
will be
by the
defined
number
by
of
the number of
number of
atoms, number
electrons
of
in the
electrons in the
excited state,
excited state,
and the
and
coefficient
the
that is
coefficient that is
A21
A21
and
and N
N2.
and 2.
Similarly,
Similarly,
Stimulated emission, what
Stimulated
is this?
emission, what is this?
Photon.
Like photon, if
We have one
we have one
electron
electron
in the
in the
excited state.
excited state,
Electron will come,
electron will come,
and then there will
and
be
then
the
there will be the
emission
emission
of
of two
photons.
photons.
And when it can
And
happen,
when it can happen, then there will be
when there will be
when
more
there will
number
be
of
more number
electrons
of
in the
electrons
excited
in the
state
excited
as
state
compared to
as
the ground
compared to
state.
the ground state.
This is we call
This
the
is we call the
population.
population inversion.
So stimulated
So
emission
stimulated
is given
emission is
by
given by
B21,
B21,
N2,
N2,
and
and rho.
and
And so there are some
relation,
important relation,
that is
that is
A21
A21
is
is
proportional
proportional to
mu cube
mu cube
B.
and B2.
So we can
So
see
we
that
can see
higher
that at higher
frequencies
frequencies,
there is one
there
knot.
is one knot.
At higher
At higher
frequencies,
frequencies,
spontaneous
spontaneous
emission
emission
will dominate.
will dominate.
So what will
So
happen
what
if
will happen if
spontaneous emission
spontaneous emission
will dominate?
will
So
dominate? So
spontaneous
if
emission
spontaneous emission will
will harder to
dominate,
make
harder to
your
make
UV
newer
rays.
UV
Okay.
layers. Okay.
Next is
Next
stimulated
is
and
stimulated and
spontaneous emission.
spontaneous
So we know
emission.
that
So we know that
spontaneous is
spontaneous is random phase,
direction,
random direction,
incoherent, and
incoherent, and
stimulated
in
photon.
stimulated photon,
The photons
the
emitted
photons emitted has
same phase,
same phase,
same
same
frequency,
frequency,
and
and
polarization
polarization
and direction.
and direction.
So these are the
So these are the
these are the
characteristics.
found
These are the
of the
foundation
laser
of the
action.
laser action.
So how can we
So
define
how
the
can we define
lifetime
the
of the
lifetime
excited
of the
state?
excited state?
So
So
so population
so
in the
population in the
so population
so population in the excited state
decreases.
decreases
And two, that
and
is the
2,
number
that is
of
the number of
photons,
photons, number of
what is
electrons, what is
the excited
in the
state
excited state
at time
at
t
time
is
t
equals
is
to
equals to
n to
n2
0 at t
0
equals to
at t
0
equals to 0
exponential
exponential minus
by
t by
gamma
gamma
to 1.
2 1.
Okay,
Okay.
topped out.
Dot.
And how can we
And how
define
can we define the
the
lifetime then?
is by 1
Is by 1 by
to 2
2 1
is equals to
is equals to
1 by 2
1 by 2
radiative
radiative
plus 1 by
plus 1 by
so there can be
so there
radiative
can be
loss,
radiative loss with a
non-radiative.
non-radiative.
So the lifetime
So
will
the
be
lifetime will be a
combination
combination of
of radiative and
radiative
non-radiative.
and non-radiative.
So
So
depending upon
depending upon that, we can
define the laser
define the laser
principle. So
principle.
what are the
So what are the
requirements for the
requirements
laser?
for the laser?
So first of
So
all,
first of all,
there should
there should
be a
be
medium.
gain medium.
What will gain
What
medium
will
do?
gain
It
medium
will
do? It
provide
will
the
provide the
in the
amplification
signal.
in the
Okay.
signal. Okay.
Amplify the.
Amplify the.
Then
Then
there should be
there should
optical
be
cavity,
optical cavity,
like just like
just like
Fabry
Fabry-Paro
cavity,
cavity,
where there will be
where there will be
mirrors.
two mirrors.
A one
A one
hundred
will be
percent
100%
and the other
reflecting,
one
and the
is
other one is
50%
99%
reflecting, and then
reflecting,
they will
and then they will
interfere there.
interfere there.
And the last
And the
condition
last
is
condition is
population.
population inversion.
That is
That is,
the number of
the number of electrons
in the
in the
excited state should
excited
be
state
more
should be
as
more
compared
as
to
compared to
the ground state.
the ground state.
That is
That is,
N2 should
N2
be
should
greater
be
than
greater
1.
than N1.
So,
So,
what is the
what
operation
is
of
the
this?
operation
One
of this?
photon
One
enters,
photon enters,
it will trigger
it
the
will
chain
trigger the
reaction,
chain
and there will
reaction,
be
and there will be
exponential growth of
exponential
photons
growth of
at
photons at
one frequency,
one
and it will
frequency, and
provide
it
us
will
a
provide
coherent.
us a coherent beam.
So,
So,
what is the
what is the
population inversion
population
and energy
inversion and
level
energy
scheme?
level
So,
schemes?
there will be a
So,
two
there will
level
be a two
system.
level
In the
system.
two level
In the
system,
two
there
level
is
system, there is
no,
no,
it's,
it's,
it is
it is
not a practical
not a
system because
practical
at
system,
some
because at
point,
some point
absorption and
absorption and emission
will balance
will
out.
balance
So,
out. So,
to have a
to
laser
have a
action,
laser
we
action,
have to
we
have three
have to
level
have three
system,
level system,
which in
which
which
in
we
to
can
which
pump
we
to
can
a higher
pump to
level.
a higher level.
So
And
the
so
condition will
the
be like this.
condition will be
There
like
is
this,
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 and there will be one
and there will be one
is a
is a
metastable state.
metastable state.
So from there
So from there it
go
can
down, and
go down, and the lasing occurs.
so in four
So
level
in four
system
level
also it
systems
will be
also, it will be
better
better,
because lasing
because lasing level
empties and
quickly
it's
empties, and
easy to
it's
maintain
easy to maintain
population.
in population inversion.
So what are the
So what
practical
are the practical realizations? So in
semiconductors
semiconductors,
use we use double
we use double
heterostructures.
heterostructures.
We use double
We use double
heterostructures,
heterostructures,
sandwiching layers
sandwiching
to
layers to
confine our
confine our
carriers and
carriers
photons.
and photons.
And population
And
inversion
population
is
inversion is
carried by
carried
we
by,
can do
like,
it
we
by
can do it
optical
by
or
optical
electrical
or
pumping.
electrical pumping.
So
So
we can easily
we can easily bridge the Einstein's early model of light matter interaction with the
laser
practical
physics,
laser physics,
showing how
showing how spontaneous versus
stimulated emission,
stimulated emission,
lifetime and
lifetime,
population
and
inversion
population inversion
can govern
can
like
govern
active
like
photonic
active photonic
devices.
devices.
So then how
So
can
then how can we
miniaturize?
miniaturize?
Why do we
Why
want
do
to
we want to
miniaturize our
miniaturize
lasers?
our lasers?
So there is a
So there is a
mismatch between
mismatch
electronic
between electronic
components,
components,
that is like
that is like
transistors and optical
transistors and optical
devices, for example,
devices, for
large
example,
lasers and
large lasers and
modulators.
modulators.
So our goal
So
is
our goal is
to integrate
to integrate
optoelectronics
optoelectronics
on chip for
on chip for
communication.
communication and
So for
computing.
example,
So for
in
example, in Intel,
Marvel is
and
also
Marvel is
working on
also working on
integrated
integrated
optoelectronic chips.
optoelectronics chips.
So what is
So
the key
what is
driver
the
for
key
this?
driver
Is
for this? This,
energy
like,
efficiency.
energy
So
efficiency. So
computation
computation
will use
will use 0.012
0.05
0.05 picojoule per bit,
data
and the
transport
data
will
transport will cost
200 to 2000
200 to
times
2000 times
more energy than
more energy than
computation.
computation.
So
So,
and we want
and we
to
want to
reduce
reduce
laser
laser
threshold, so that
threshold,
will
so that will
eventually
eventually reduce
energy per trans.
energy per transmitted bit.
So what are the
So, what are the
challenges
challenges
with the
with
conventional
the
lasers?
conventional lasers?
So
So,
for the
for the
traditional
traditional edge
emitting lasers,
emitting lasers,
we
means
are
we are
incidenting
incidenting light
at the edge of
at
the
the edge of
meters,
the emitters,
and but
but the
threshold was
threshold was in
milliwatering.
milliwatering. That's a very high energy.
And for high
And for
data
high
rate,
data
for
rates,
example,
for
10
example 10
gigabytes per second,
gigabytes
it
per
means
second, it means
picojoules per bit.
picojoules
That is
per
very
bit.
high.
That is very high energy.
But
But
photodetectors can detect
photodetectors can
femtojoule
detect
pulses.
femtojoule pulses.
But
But
photodetectors can detect
photodetectors
the
can detect the
femtojoule pulses.
femtojoule
So
pulses. So
laser
laser
inefficiency is the
inefficiency is
bottleneck.
the bottleneck.
Why
So
threshold is
why
high?
threshold is high?
Because of the
It's
device
because of the
size.
device
So the
size.
device
Because the
size is
device size is
of the
of
10
the
order of the
10 order of the
hundreds
10
of
to hundreds
microns.
of microns.
And if the
And
device
if
size
the
is
device size will be large, it means
large
there will be
volume,
large volume
so
that
large
so
volume will
large
require
volume will require
high pumping
high pumping
to achieve
to
the
achieve
population
the
inversion.
population
That was the
inversion. That
necessary
was the
condition for
necessary
glazing.
condition for
So
glazing.
what
So
is the
what
solution?
is the solution? So
We can
we can
shrink the laser
shrink the
cavity,
laser cavity
so that we need
so
to
that
pump
we need to
smaller
pump
region, and
smaller
then we
region,
can
and
get
then
a
we can get the
lower threshold.
lower threshold.
So
So
then we
then
work
we work
on the, like
on the, like
people started
people started working on the scaling
down
down
the size of
the
the
size
cavity.
of the cavity.
And
And
first they
first they in 1960s
they
they
so there were
so there were edge emitting
lasers where
lasers where
there was large
there was
volume
large
as
volume
emission
as
threshold
emission
high, and
threshold high,
figure of
and
merit is
figure of
given by
merit is given by
volume by lambda.
volume by lambda cube.
So
So
then
then
the
then the
alternative, like after
alternative, like after
1960, after
1960s,
edge emitting
after edge
lasers
emitting lasers,
came
it came
in
in
1978,
1978.
PCSELS. This means
PCSELS. This
vertical
means
cavity
vertical
surface
cavity
emitting
surface
lasers.
emitting lasers.
It came into
It came
picture
into picture
where we were
where
using the
we were using the
topless
DBR
bottom
topless bottom
that will act as
that
a
will act as a
cavity, and it will
cavity, and it will
confine
confine
vertically,
vertically,
and
and
will
light
emit
will emit
upwards in the upward
upwards in the
direction.
upward
So we
direction,
can
so
easily
we can
integrate
easily
on.
integrate onto.
It was
So
10
it was
times
10
smaller
times
than the
smaller than the
ELs,
ELs,
edge emitting
like edge
lasers.
emitting lasers.
After
After
vertical
after
cavity
vertical cavity
lasers,
lasers,
microdisc lasers in
microdisc lasers in
1990s came,
1990s came,
and it was a
and it was a
semiconductor disc which
semiconductor disc
had
which
size of
had
5
size
to
of
10
5 to
micrometer.
10 micrometer.
And
And
we saw
so
that
we saw that
in micro
in
lasers
micro
with
lasers with
WGM, whispering
WGM,
gallery
whispering
modes
gallery
were
modes were
propagating
propagating
at the
at the
periphery of the
periphery
disc.
of the disk.
So it means
So it means
we are
we are
incidenting light
incidenting light
after entering
after
into
entering
the disc,
into the
after
disk.
coupling with
After
the
coupling with the
semiconductor.
semiconductor,
It will circulate
it will
along
circulate along
the periphery
the
of the
periphery
disc,
of the disk,
and it is
and it is
much smaller in
much
size,
smaller in
but
size,
still there
but
was
still there was
it's limited.
it's limited by the diffraction effect.
After
After
microdisc lasers,
microdisc lasers,
photonic crystal
photonic
cavity
crystal
lasers
cavity lasers it
came in
came in
2000.
2000.
So
So
what
what
what was the
what was the
advantage of this?
advantage of
That
this?
the gain
That the
medium
gain
itself is
medium itself is
embedded in the
embedded in
photonic
the
band gap
photonic band
structure,
gap
so that
structure, so
there
that
will be a
there will be a
there will be
there will
strong
be
confinement.
strong confinement.
But still,
But still,
the overall
the overall
cavity size
cavity
was still
size was
tens of
still tens of
microns.
microns.
So then
So then
nanowire lasers
nanowire
came.
lasers came.
So
So
in
in
in this case,
in this
the
case, the
semiconductor
semiconductor
nanowires were
nanowires
acting
were
as
acting as
cavities, and
cavities, and
it had
it
a
had
some micron
some
diameter.
micron diameter.
But still, the
But
problem
still, the
was
problem was
it was
it
limited
was
by
limited by
the
the
friction.
diffraction.
So what was the
So what was
limitation
the
in all
limitation
these
in
things?
all
That
these things?
all
That
these
all these
cavities
cavities
were
were
dielectric based,
dielectric
so that
based,
we
so
can
that we
find
can
the light
confine the
only up to
light
the
only up to
diffraction
the
limit.
diffraction limit.
So
So
what is a
so
big
what is a big
breakthrough here?
breakthrough here?
So we introduced
So
the
we introduced the
plasmonic
plasmonic
nanolasers.
nanolasers.
It was
It
proposed
was
by the
proposed by the Stockman
in
and Bergman in
2003
2003
and
and
demonstrated
demonstrated in 2009
by Shalley.
by Shalev Group.
So what did they
So, what did
use?
they use?
The
They used the
metal dielectric
metal dielectric
structures in
nanostructures
which
in which
they introduced the
they
surface
introduced the
plasma
surface plasmon
polaritons
polaritons
that are
that are
we talked
SPSPs. We
about
talked
these in
about these
previous,
in previous weeks.
so that can
So that
confine
can
light
confine
below the
light
diffraction
below the
limit.
diffraction limit.
So what were
So
the
what were the
advantages of that?
advantages
So
of that? So
we can have the
we can have
dimensions
the
of
dimensions of
sub-wavelength cavities
sub-wavelength cavities,
and
and
lasing
lasing
threshold
threshold
can be reduced.
can be reduced.
Two main
So two
advantages
main
of
advantages were
sub-wavelength cavities
sub-wavelength
and lower
cavities and
threshold
lower
possible.
threshold possible.
So
So the
examples.
examples
So the
so the
examples
examples
of
of
these
these
cavities
cavities
like are
like are
electrically pump
electrically pumped
nanoscale lasers
nanoscale
which were
lasers, which were
demonstrated
demonstrated in
which was
which was
demonstrated in
demonstrated in
2007.
2007.
And what did
And
they
what did
use?
they use?
So
So
initially we were
initially we
dealing
were
with the
dealing with the
dielectric
dielectric
nanostructures,
nanostructures,
but these were
but these were
limited by the
limited by the
diffraction. So we
diffraction.
could
So we
not
could not
confine our
confine
light
our
in the
light
sub
in the
wavelength range.
sub-wavelength range.
So then
So
we deal
then we
with the
deal with
metal
the metal
dielectric
dielectric
semiconductors
semiconductors
heterostructure
heterostructure,
because we saw
because
in
we
the
saw in
previous
the
lectures
previous
that
lectures that
uh,
uh,
we can
we can
confine our
confine
light
our
in the
light in the
sub-wavelength range
sub-wavelength range
without any
without any
diffraction.
diffraction limit.
So in
So
that
in that
metal,
metal,
in the
in the
heterostructures where
heterostructures
we are
where we are
sandwiching
sandwiching
the
the
metal
metal
dielectric
dielectric
semiconductor,
semiconductor,
so we
so
can
we can
electrically
electrically inject
carriers,
carriers,
so they
so
will
they will
recombine
recombine,
and
and then
after
after
recombination they can
recombination they can
release.
lase.
So
So
two
two
advantages of
advantages
that
of that,
we can
we can
have the
have the
lower
lower
threshold
threshold
value that
value that
earlier days
earlier
it
days
was
it
order
was
of
order of
microwatt.
microwatt.
Now we
Now
can
we can
reduce it.
reduce it.
So
So,
and the
and the
size of
size
the
of the
laser
laser
is
is
also
also
around
around
500
500
nanometer.
nanometer.
That
That
was
was
in
in
earlier
earlier
previously
previously
it
it
was the
was the
order
order
of
of
10
10
micron or
micron or
100
100
micron.
micron.
So
So
the
the
two
two
most
most
important
importantly we have
limitations we
limitations we
have
have
covered
covered
from
from
dielectric
dielectric
to
to
plasmonic
plasmonic
lasers
lasers,
that
that
we
we
are
are
reducing the
reducing the
laser
laser
threshold
threshold
as
as
well as
well as
the
the
miniaturization
miniaturizing
miniaturization of
miniaturization
the
of the
cavity.
cavity.
So
So
which
which
is
is
like
like,
so what
so
is
what
the
is the
signature
signature
of
of
the
the
lasers?
lasers?
So
So
first we
first
will
we will
have the
have the
spontaneous
spontaneous
emission.
emission.
Suppose we
Suppose
are
we are
going like
going like
this.
this.
Then
Then
one is
one is
like
like,
then there
then there
always comes
always
a
comes a
kink.
kink.
So if
So if
something is like
something is like
coming,
coming,
then we
then
can
we
say
can
that
say that
here we have
here we have
spontaneous
spontaneous
and here
and
we
here
have
we have
the
the
stimulated emission.
stimulated emission.
The other
The
thing
other
is
thing is,
earlier we
earlier
have
we
like
have like
this.
this.
So it
So
will
it
define
will
as
define as
it is
it is
FWHM,
FWHM,
which
which
defines that.
defines the,
So what does
so what does
FWHM
FWHM?
define?
It
The
defines the
quality factor
quality
of the
factor of the
cavity.
cavity.
So if
So
it
if it
is
is
narrow,
narrowing,
if it
if
is
it is
coming
coming very
sharp
sharp
peak,
peak,
if it
if
is
it is
very
very
sharp
sharp
peak,
peak,
then the
then the
Q
Q
factor
factor
increases.
increases,
Meaning we
meaning
are
we are
getting
getting
the
the
glazing
glazing
peak
peak
above the
above the
threshold.
threshold.
So we
So
see
we saw
that
that
nanoscale
nanoscale lasers,
we
we
have
have
like there was
like there was the
evolution of
evolution of
nanoscale lasers
nanoscale
from
lasers
edge
from
emitting,
edge emitting,
then vertical
then
cavity
vertical
surface
cavity
emitting
surface
lasers,
emitting
then
lasers, then
microdisc, then
microdisc, then
photonic crystal
photonic crystal
cavities,
cavities,
then
then
nanowires,
nanowires,
and then
and
from
then
that
from that
nanowires tube
nanowires
got
tube
the
we got
plasma.
the plasmonics lasers.
So
So
plasmonics enable the
plasmonics enable the
sub-wavelength
sub-wavelength
confinement and
confinement and
potential
potential
for ultra
for
low
ultra
threshold
low
and
threshold
on-chip
and
lasers.
on-chip lasers.
So,
So,
but what was the
but what
problem
was
in
the
that?
problem in that? So
They,
there,
it is still
it is
lacking
still
a robust
lacking a
design with
robust
3D
design with
confinement
3D
plus
confinement
electrical
plus
pump.
electrical pump.
So for
So
that, what
for
can we
that,
do?
what can we
We
do?
can make
We
a
can make a
metal context
metal context,
plus we can do the
plus
dot.
we can make a dopings.
Metal, what
So
will
metal,
metal
what
do?
will metal
There
do?
will be
So
metal
there will be metal
semiconductor context
semiconductor
that will
context
form
that
a
will form a
Schottky barrier that
Schottky barrier that will add
resistance, and it
resistance, and it will
reduce the
reduce
efficiency.
the efficiency.
What
So,
is the solution?
what
We
is the
can
solution? We
heavily
can
dose.
heavily dope.
We can dope
We
heavily
can dope
of the order of
heavily of the
10
order
to
of
the
10
power
raised
18
to
to
power
10 to the
18
power
to 10 raised to
19
power
per
19 per
centimeter cube
centimeter
at
cube at
contact region
contact region
to narrow
to
down the
narrow down the
so
barrier,
that the
and so that the
tunneling can
tunneling
happen,
can happen,
which will
which will
which will enable
which will
efficient
enable
carrier
efficient
injection.
carrier injection.
And also
And also,
we can do the
we can do
careful
the careful
by carefully
by carefully
designing the
designing the
context for P
context
type
for
and N
P
type
type and N
is
type
very
is
crucial
very
for the
crucial for
efficient
the
injection.
efficient injection.
So
So,
so we can
so
say
we can say that
miniaturizing lasers
miniaturizing
is
lasers
critical
is
for
critical for
reducing
reducing
data transport
data
energy in
transport energy
computing
in computing,
and
and
advances from
advances
VC
from VC
vertical cavity
vertical cavity vertical
surface
cavity
emitting
surface
lasers
emitting
to
lasers
plasmonic
to plasmonic
nanolasers. It shows a
nanolasers. It
great
shows a
high
great
progress
high
towards
progress towards the
nanoscale,
nanoscale,
low threshold,
low
and
threshold,
integrated
and
light
integrated
sources.
light sources.
So
So,
next
next,
we will see
we will
what are
see what are
electrically driven
electrically
nanowire.
driven nanowire
What
lasers.
are the
So,
main
what are the main?
so if
So,
we are
if
using
we are
metal,
using
then
metal,
how
then how
will light
will
escape?
light escape? Okay,
So
so
we are
we
not
are
using
not
too
using
thick
too thick
metal
metal
thickness like
thickness
100
like
nanometer or
100
200
nanometer or
nanometer. We
200
are using
nanometer. We
just
are using just
50 or 40 or
50 or
20
40 or
nanometer
20
because
nanometers. So,
this
this
thin
thin
top metal will
top
allow
metal will
partial
allow a
transmission
partial transmission,
because the skin
because
depth
the
of
skin depth
metal
of
is of the order of
metals is of the order
145
of
nanometers
145 nanometers
like
and
this. So
like this. So,
if we have
if we have
20 nanometer thick,
20 nanometer thick or 50 nanometer
light
thick,
can easily
light can easily
transmit to
transmit
the metal.
through the metal.
Or we can
Or we can we
do
can
careful
do
engineering
careful engineering
or
or
create a balance
create a
between
balance between
reflection and
reflection and
transmission that will
transmission,
make
that
a
will
good
make the
cavity
good
and
cavity, and then
output coupling
output
reason also
coupling
we can
reason
have the
also we
great
can have the
transmission.
great transmission.
Then
Then,
arrays
nanoparticle
and P
arrays and
resonances.
me
So
resonances. So,
for these
for
we
these,
have the
we
gallium
have the
arsenide
gallium
nano
arsenide nano
antennas,
antennas,
200 nanometer
200
diameter,
nanometer diameter and 250
height.
nanometer
If
height.
we are
If
arranging
we are arranging in the periodically,
then the
then
whole will
the
work.
whole will work.
So and
So,
how it will
and
work?
how
So
it will work?
dipole
So,
emission,
dipole emission.
single
So, single
dipole radiates in
dipole
dot
radiates in
pattern,
donut
no
pattern. There is
vertical
no
emission.
vertical emission.
So
So,
arrays will
arrays
enable
will
the collective
enable the
effect that
collective effects, that is,
create
it can
directional
create a
emission,
directional emission by
constructive
constructive
interference, and
interference. And
so
so,
subdiffractive arrays
subdiffractive
because
arrays, it will,
the
because
diameter is
the
of
diameter is of sub
200
wavelength,
nanometer
200
diameter,
nanometer diameter and 250
height.
nanometer height.
So
So,
it will
it will
suppress the
suppress
diffraction
the diffraction,
and the
and the
radiations will be
radiations will
trapped
be trapped,
and
and
it will lead to
it will
the
lead to the
bound states in the
bound states in the
BIC.
container
We will,
BICs.
uh, we will see the
We will
various
see the various
examples.
examples of this.
So how can
So,
we
how can
improve
we
the gain?
improve the gain?
Optical gain.
Optical gain. So,
Intrinsically,
intrinsically
in gallium
in
arsenide,
gallium arsenide,
there's very low.
there's very low gain. So,
We cannot
we cannot
make
make
a
a
glazer
glazer with
intrinsically gallium
intrinsically
arsenide.
gallium
We
arsenide.
have
Like, we
to.
have to do.
Okay,
Okay.
so
So,
and why is this
and
so?
why is this so? Because
There's an effective
there's an
mass
effective
mismatch. So
mass mismatch.
electrons
So,
have small
electrons have
effective mass,
small
so
effective
that
mass,
quasi
so that
Fermi level
quasi
moves
Fermi
deep
level
into the
moves deep
conduction
into the
band. But
conduction
in
band.
case of
And but in
force,
case of force,
there's a large
there's a
effective mass
large
and
effective mass,
quasi
and
Fermi level
quasi
stays
Fermi level
shallow in
stays
the
shallow in
valence
the
band.
valence band.
So
So,
because of
because of this
imbalance,
imbalance,
effective mass
effective
mismatch,
mass
there's a
mismatch,
poor
there is a poor
population inversion.
population inversion.
So,
So,
what is the
what is the
experimental
experimental demonstration
demonstration
of
in
glazing
arrays?
in arrays?
So we
So we
so we will
so we will
pump optically
pump
with
optically with
femtosecond laser
femtosecond laser
below threshold,
below
that is
threshold,
broad
that is broad
spontaneous emission.
spontaneous emission,
And if
and
we are
if
moving
we are
above the
moving
threshold,
above
we
the
will get the
threshold, we will
narrow
get the
lasing
narrow lasing peak.
peak. And
And
in this
in
structure,
this
I want to
structure, I
show.
want to show you.
Yeah,
Yeah,
here.
here.
So
So
so you can see
so
that
you can see that
the quasi
the
Fermi
quasi
level in
Fermi
case
level
of
in case
conduction
of
band,
conduction band,
it's in
it's
that
in
region.
that region.
And here,
And
this
here
match
there's a
in the
mismatch
effective
in the
mass of
effective
force
masses of
electrons
holes
will
and
limit the
electrons will
optical
limit the
gain in the
optical gain in the
semiconductors.
semiconductors.
So
So
when we are making
when we are
such
making
structures,
such
then we
structures, then
here
we
they
here
got the
they got the
Q value.
q
Q
value
factor is
q
equal
factor
to
is equals to
2700 and
2700,
the lasing
and the
threshold is
lasing
10
threshold is
microjoule
10
per
microjoule per
centimeter square.
centimeter square.
So light
So light
LL curve.
LL
You can see
curve,
that
you
light
can see that
in
light in
versus light
versus
output
light output
will show the
will show
S-shaped
the
transition
S-shaped
that will
transition
confirm
that
the
will
lasing.
confirm the lasing.
So
So
emission line width
emission line
will
width
narrow
will
to
narrow
1
to 1
nanometer above
nanometer
threshold.
above
And we can
threshold, and
also
we can also
calculate the G2,
calculate
that
the
is the
G2, that is the
correlation second order
correlation second
correlation
order
measurement
correlation
that will
measurement,
confirm
that
if
will
G2 is
if
equal
G2 is equals
to
to
1.
1.
So
So
if G2
if G2 is equals to 0,
is equals to 1,
is equals
it
to 1,
implies
it implies the
coherent.
coherent lasing.
What are the
What are
limitations
the
of this? So
limitations of
it
this? So it
works only at
works
low
only at
temperature,
low
that is
temperature, that is
77 Kelvin,
77 Kelvin,
and the threshold
and
is
the
high
threshold
due
is
to
high due to
insufficient optical
insufficient
gain,
optical
and
gain, and
we have to
we
do
have to
optical
do
pumping
optical
only. So
pumping
that is
only. So that is
impractical for real
impractical for real
devices.
devices.
So there
So
are
there
many
are
solutions
many
to
solutions to
improve the gain.
improve the
The
gain. So the
solution for
solution
improving
for
gain is
improving gain
p-type
is
doping.
p-type doping.
So okay.
Okay.
So what
So
does it mean?
what
So
does it
what
mean?
will
So what will
I
it do
am
if I
doping?
am
Then
doping? Then
it will
it will
move
move
the
the
equilibrium Fermi
equilibrium
level
Fermi level
closer to
closer to
valence band.
valence band.
What will
What
it
will
give us?
give
So
us? So
now the better
now the
overlap of
better
quasi
overlap of
Fermi
quasi
levels.
Fermi levels.
And that will
And that
provide us
will provide us the
stronger gain.
stronger gain.
And the next
And the
thing is
next thing is
train engineering.
training. So
what does it mean?
what does
So
it
if
mean? So
we
if we
gauge
gauge
the strain,
the strain, including
strain
strain
in our device,
in our
what will
device,
it
what will
affect?
it
Will
affect?
change
It will change.
it will change
It will
the
change the
curvature.
band curvature.
And
And
we know that
so we know that
the band
if the
curvature,
band curvature will change, then the
effective mass
effective mass will change, and that will improve
the mobility.
the mobility.
If mobility
If
will
mobility will be
improve,
improved, then optical gain will automatically.
and next is
Next is
surface passive.
surface passivation.
So what does this
So
mean?
what does this mean? So
We want
we want to have the non-radiative
so the
set.
non-radiative
The
means they are
non-radiative
not,
means they are not
there is no photon. The energy is converted into heat.
converted into heat, or
There is the emission of
the
photon.
emission of photons because of this.
So we want to
So we want to remove
non-radiative
non-radiative
surface states.
surface states.
Okay.
Okay.
So now
So now
the surface
the surface
recombination
recombination
is a key
is a
limiting
key
factor.
limiting
So in the
factor. So in the
nanostructures,
nanostructures,
in case of
in case of
nanostructures, there's
nanostructures,
a large
there's a large
space to volume.
surface to volume ratio.
So that
So that
there are
there are
surface.
many surface states.
And
And
these states are
these states are
act as
act
these
as
surface states
these
act
surface
as
states act as a
non-radiative
non-radiative
recombination structures
recombination structures
that increases the
that
threshold.
increases the threshold.
So
So
gallium
gallium
arsenide
arsenide
has very
has very
high
high
surface
surface
recombination.
recombination centers.
That increases
That
the
increases
threshold.
the threshold.
That increases.
That increases the lasing threshold.
So that's why
So that's why gallium arsenide is not
nice, poor
nice. It's a
material.
poor material for nano laser.
Then
Then
what should be the
what
better?
should be the
So
best
better.
material? So better.
So
So
better materials
better
are
material for
indium phosphide,
indium phosphide,
INP,
INP,
gallium indium
gallium
phosphide,
indium phosphide,
GI.
GIMG.
So these
So
materials
these
have
materials have
lower surface
lower surface
combination
recombination
velocities.
velocities.
So
So
switching.
switching.
So
So
if they
so
have
if
lower
they have lower surface
recombination,
recombination,
it was
it
the we will
was
get
the
the
we will
lower
get the lower threshold
polarizing.
for lasing.
Okay.
Okay.
So at a
So at a
nanoscale,
nanoscale,
we have
we have
the
the
constant
constant
flux
flux
of
of
carriers
carriers
from
from core
core to surface,
to
and
surface,
it will
and it will
recombine via
recombine via
surface states.
surface states.
So we are
So we
describing
are
it as
describing it as
velocity.
a velocity.
That is the
That
effective
is the
speed at
effective
which the
speed at
carriers
which the
are
carriers are
swept into the
swept
surface
into the
traps.
surface traps.
So
So
we can
we
conclude
can
that the
conclude that
high
the
surface
high surface
recombination velocity.
recombination velocity.
Okay, so
Okay, so
that is
that
high
is
SRV
high
surface
SRV surface
recombination velocity
recombination velocity
is equals to
is equals to
rapid
rapid
non-radiative losses
non-radiative losses
is equals to
is
high
equals to
threshold.
higher threshold.
So we want
So
to
we want
avoid
to
this.
avoid this.
So that's why
So that's why
we want the
we want the
lower threshold
lower
for
threshold for
lasing. And
lasing
for
for
that,
and
we
for
want
that we want
to
to
suppress the
suppress the
non-radiative
non-radiative
combination, and for
combination,
that
and
we
for
have
that
to
we
lower
have to lower
surface
surface
recombination velocity.
recombination velocity.
So,
So
like, what
like
do we want
what do
for
we want
material
for
engineering?
material
We have
engineering?
to
We
choose
have to
materials
choose
such that
materials
which
such
have low
that which
SRV
have low
materials,
SRV materials,
and
and
for doping,
for doping
especially we will choose
especially
the
we will
P type
choose
for
the
better
P type
gain,
for better
and
gain,
for
and
strain
for
we have to
strain we
modify
have
the
to
band
modify the
curvature
band
that will
curvature that will
automatically improve
automatically
mobility
improve
and gain,
mobility and gain.
and for
And for
passivation
passivation we
reduce
will reduce
surface state to
surface state
suppress
to suppress
non-radiative
non-radiative
recombination.
recombination.
And regarding
And regarding
designing,
designing,
we have to go
we have to
beyond
go beyond
classical, so
classical,
that is
so that is
sub-wavelength and
sub-wavelength
high-Q
and high
designs.
Q designs.
So we saw
So
that
we
like
saw
how
that like how
nanoparticle arrays
nanoparticle arrays
it
and
can enable
it can
lasing,
enable
but
lasing, but
challenges remain
challenges
high
remain in
threshold
higher
and
threshold
also
and
poor
also
material
poor
choice
material choice and
and non-radiative losses.
non-radiative losses.
So we
So we
need some
need
progress in
some
the
progress
direction
in
of
the
how
direction of
can we
how can we
doping,
doping,
how can we dope
how
our
can we dop
materials
our
so that
materials
we
so
can
that we
get
can get
the low
the
threshold,
low
and
threshold,
how can we
and how
engineer
can
the
we
strain
engineer the strain
and surface
and
specification
surface
and better
specification and
material
better
selection
material selection
for practical
for practical
nanoscale lasers.
nanoscale lasers.
So
So
the next
the
is
next is
from so
from
non
so the non
nanophotonics
nanophotonics
resonators were the open
resonators were
system, that
open system.
is,
That is,
so in general we
so in
deal with
general we
the
deal with the
Hermitian system.
Hermitian
What does it
system.
mean
What
Hermitian
is in the
system?
Hermitian system?
That
That
energy is
energy
conserved,
is conserved,
eigenvalues are real,
eigenvalues are real,
and
and
we saw that
we saw that
case of the
in case of
isolated
the
disk
isolated disk
resonators,
resonators,
where we have
then
the
we have the
narrow
resonances
line
with narrow line width and higher Q.
So, but at
So, but at
nanoscale,
nanoscale,
these are open
these are
system
open
because
system because
energy leaks
energy leaks
into the
into
surrounding.
the
So that
surrounding, so that
material losses
material
plus
losses
radiative
plus
losses.
radiative losses.
So
So
and so
and
then
so
in
then
the case of
in the case of
so we
non-Hermitian
have the
system, we will have
complex
the complex
eigenvalues, and it will
eigenvalue,
lead
and it will
to
lead to
broadened line
broadened
width.
line widths.
That is,
That is,
we will get
we
the
will
low Q
get the
factor.
low Q factor.
So there
So
is a
there is a
challenge.
challenge
Hard
is
to achieve
hard to
sharp
achieve
resonances
sharp
in single
resonances in single
nanostructure.
nanostructure.
So
So
because lasers are
because lasers are
because
non-Hermitian
here we are
system, because here
considering
we
the
are considering
material
the
losses
material
plus
losses
radiative
plus
losses,
radiative losses,
and there is
and
extra
there is
gain also.
extra gain also.
So what is the
So
idea?
what is the
The idea is
idea?
to
The idea is
combine
to
gain
combine
and loss.
gain and
So
loss.
the
So
conventional
the
view is
conventional
loss
view
is
is loss is
undesirable, so
undesirable, so that will
increases the
increases
bandwidth,
the
broadens
bandwidth,
the line
broadens
and
the
lowers the
linewidth, and
Q.
lowers the Q.
How can we define
How can we define the
optical potential
optical
in terms of
potential
this?
in terms of this?
So
So
if we
if
have the
we
complex
have the
refractive
complex
index,
refractive
that is,
index, that is,
if gain and
if
loss
gain
are
and loss are
balanced and
balanced
engineered,
and
new
engineered,
physics will
new physics
emerge.
will emerge.
And
And so
nx,
nx,
so
so
nx is equals
nx
to
is
n
equals to
real
n real
plus iota
plus iota
n imaginary.
n imaginary.
So its
So its
real part
real
is
part is
even function
even function
that
that will
mirror symmetry,
mirror symmetric,
and the
and the n
imaginary part
imaginary part
will be
is will
odd
be
function.
odd function.
What does it
What does it mean?
gain
That
on
is
one
gain
side,
on one side,
loss on the other?
loss on the other.
So the system
So the
we
system,
deal with the
like we deal
parity
with the
symmetry,
parity
time
parity time PT symmetry system.
So
So
even
even
we have the
we have the
non-orthogonal, even
non-orthogonal,
we have the
even we have the
non-Hermitian system,
non-Hermitian
we
system,
can still
we can
have the
still
real
have the real
eigenvalues and
eigenvalues, and we
realize
can
physically
realize
it.
physically it.
So
So
we can
we can
make the
make
structure.
the structure.
How can we
How
realize
can we realize it
structure
physically?
is equal
Structure is equals to
to gain medium
gain medium
plus loss
plus
medium,
loss medium,
and it was separated
and it
by
was separated by a thin
dielectric spacer.
dielectric spacer.
So example
So example is
indium,
indium
gallium,
gallium phosphide,
IgG.
INGAP.
So same
So
material
same
but
material
differently
but
doped. So we
differently
can
doped.
dope
So we can dope with
we can
we can
dope with N
dope
type.
with N type.
So for
So
intrinsic
or
loss
intrinsic
absorbing
loss
and P
absorbing,
type,
and P
we
type
want to gain
we want to
amplify.
gain amplify.
So in we
So
are
in we
arranging
are
these
arranging these
dimers in the array
dimers in
form,
the
so it
array
will
form, so
behave
it
like
will
a
behave like a
nano antenna
nano
lattice with
antenna
extra
lattice with
degrees of
extra
freedom.
degrees of freedom.
So
So
what are the key
what are the
optical
key
properties?
optical properties?
Okay, let's take
Okay, let's
10
take
minutes,
10 minutes
then
break,
I will
then I will
resume this.
resume this.
Okay, so I was
Okay, so I
telling you
was
that how
telling
can
you
we
that how can
physically
we
realize.
physically realize.
How can we
How can we
physically realize
physically realize
the laser?
the lasing?
So we have
So we
a
have
material
a
which
material
is
which is
one is p
one
dot
is
and
p
another
dot and other
is
is
n dot.
n dot,
In
and
between
in
there's a
between
special
there's a
layers.
special
We
layers,
are
and we are
arranging these
arranging
in
these
the form of
in the
array
form
so
of
that
array so
we can
that
have
we can
it
have
will behave
it
like
will
a nano
behave like a nano
extra
antenna
degree
with
of
extra
freedom.
degree of freedom.
What are
And
the key
what are the
optical
key
properties
optical
of this?
properties for this?
So one is
So one is
light incident.
light incident.
So first
So
is
first is
asymmetric
asymmetric
reflection
reflection
or
or
transmission.
transmission.
So light
So light incident from
versus
gain
loss
side versus
it
loss
will give
side,
you the
it will give you the different
right?
response. Okay.
And the second
And the
is
second is
resonance.
mirror resonances.
That is
That is, it
enhanced
will enhance
directional
the directional
scattering.
scattering.
inside
inside
gain loss
gain loss
we
structure.
have
That is, we have engineered our gain loss
material
in the
such that
material such that
we are getting
we are getting the enhanced directional
scattering.
scattering.
Third
And the
is
third is
lattice.
lattice resonances.
So
So,
like we are
like we are doing a,
we are arranging
we are arranging
we are arranging
we are arranging our structure in a periodic
array
array
that will give us
that will give
sharp
us a
resonance
sharp resonance
with high.
with high Q.
So
So
we will calculate
we will calculate the
the
response,
reflection.
the reflection and transmission spectra.
It will show
It
you.
will show you.
So in the
So in the PT symmetry,
this
this
under the case of
under the case of
asymmetric
asymmetric scattering, we are
doing two cases
doing two
direction
cases:
high.
directionality and high cavity cavity. If we are talking about directionality, then
We will talk
we
about
will
the
talk about the me resonances, and if we want high Q cavity, then we'll talk about the
lattice resonance.
lattice
In this
resonance. So
case,
in this case, you can see that
in case of
in case of
asymmetric
asymmetric transmission in
gradient,
gradient metasurfaces,
so at certain
so at
gaps
certain gaps
plus at certain
plus at
wavelength,
certain
we are getting
wavelength, we are getting that
big
big
GAN trans.
giant transmission peaks.
So that will
So that
correspond
will
to the
correspond to the spectral
similarities. Where,
singularities. Where
so what are the
so what are the spectral singularities? The
mathematical
mathematical
degeneracy
the
point where
degeneracy
output
point where
diverges
output diverges,
and the Q
and the Q factor,
uh, factor
the Q
the
factor,
calculated
the calculated Q factor with this
is
structure is
10 raised to power
10 raised
5.
to power 5.
So which
So
was
which was 2 raised
2700
2700
experimental.
experimented with simple arrays.
So
So
means that
means that was not
there was no
there was
balance
not
in gain and
balance in
loss.
gain and loss.
So we can say
So
that
we can say that
there's a rob
there's a
the structure is
this
robust
structure is
against
robust against
fabrication
fabrication
that
variation
doesn't require
that
the
doesn't
exact
require the
spacing.
exact spacing.
So
So
we can get
we
the
can get the directional
and also
scattering, and also we
with the
can tune the
resonance. So
resonance.
by
So
introducing
by introducing the
gradient
phase
metasurface,
gradient metasurfaces,
earlier we talked
earlier we talked about it today.
so
So
we will have the
we will
array
have the array of nano antennas
varying
with
size and
varying
orientation
size and orientation,
so that if
so
light
that
will
if
enter
light
from
will
loss
enter
side,
from loss side,
this will scatter
this will scatters into the
zero diffraction
zero diffraction order, and if
from the
light
gain
enters
side,
from
it
the
will
gain side, it
scatter
will
into the first
scatters into the
diffraction
first
order.
diffraction order.
And if we will
And
pump,
if we
it
will
will change
pump,
the
it will change the
balance,
gain loss balance, and it will
enable
enable
the
the
tunable scattering.
tunable scattering
So
directionality.
what are the
So
key
what are the
takeaways
key
of this?
takeaways of
So
this?
we can say
So we
that
can
loss
say
is
that
not
loss is
always
not always
harmful.
harmful.
Okay,
Okay,
so
so
we can
we
in
can in
symmetric
PT
system
symmetric
we are
system we are
combining gain and
combining
loss
gain and
that
loss
will give
that will give
the new design.
the new design freedoms,
It
and
will
it will enable the
high
ultra high
factor,
Q factor,
asymmetric transport,
asymmetric
and
transport,
directional
and
tunable.
directional tunable emission.
So
So
today
today
this clause
this
is
clause is a discussion on tunable and active
phase.
metasurfacing.
Next we will talk
Next we
about
will talk about the how atom
with
dipole interact
cavities.
with cavities,
That is cavity
that is cavity
quantum
quantum electrodynamics at
scale and
nanoscale, and
how
how
the
the
transition, how
transition how
like the transition
there is a
into
transition
quantum
into
resin
quantum resin
plus a brief
plus a brief
description of
description of
nanofabrication.
nanofabrication technique.
So we saw
So
that
we saw that
not
in non-Hermitian
by
photonics,
carefully
by
balancing
carefully
gain and
balancing
loss
gain and loss
in
in
nanostructure, we can
nanostructure,
achieve
we
the
can
real
achieve the real eigenvalues,
ultra high Q
ultra
factor,
high Q factor,
asymmetric transport,
asymmetric transport,
and tunable
and
scattering.
tunable scattering.
So these are
So these
all
are
key
all
ingredients for
key
next
ingredients for next
analysis.
generation nanolasers and metasurfaces.
So
So
next we will
next
solve
we
the
will
assignment.
solve the assignment. So
we have
we have
the table.
in the
We have
table, we have a table below
different
different
mechanisms
mechanisms
related
related to the generation and recombination of electrons.
to all where are
All
given.
where are given.
So
So
we saw that
we saw that in case of absorption,
an electron
an
will come,
electron will
a
come,
photon will
and
come, it
photon
will
will come, it
interact
will
with
interact
electron.
with electrons.
So it is a
So
ground
it is a ground state, it is
excited
an
state.
excited state.
So
So this is
like this,
like this. In this, it is represented as 1 and 2.
so this is
So this is
absorption.
absorption.
In the option
In the option
A, so
A,
this is C.
so this is C.
In the option
In the
A, they are
option
showing
A, they are showing that
here are
here are
electrons
electrons
and here are
and here are holes.
electrons are coming
Electrons are
from
coming
excited
from
state to
excited
ground
state to ground state,
and the photon
and the
is
photon
emitting
is
out.
emitting
So
out.
this is a
So this is representing the
spontaneous.
spontaneous emission.
So option
So option,
so A will
so
match
A will match the
second.
second.
In the B,
In the B,
in the B
in the
option,
B option,
there is a
there is a
metastable state.
metastable state.
The electron
The
first
electron
coming
first
to this
coming is
and
to
then
this and then
coming to the
coming into the ground state.
and this
And this
electron.
electron,
So this is the
so this
example
is
of
the
trap
example of
assisted
trap assisted
recombination.
recombination.
And the last
And the last
D,
D,
electrons are in the
electrons are in the
more number of
more number
electrons
of
are in the
electrons are in the
excited state.
excited
It
state,
is
and it is
when it is moving
when it is
from
moving from
when there is a
when there
transition
is a
from excited
transition from
state to
excited state to
there are
ground
the
state,
emission
there are the
of
emission of two photons.
so that is
So that is,
the
it represents the
stimulated
stimulated
emission.
emission.
So the
So
answer is
the answer is
A option
A option
matches second.
matches second.
First figure is
First
showing
figure
the
is showing the
spontaneous emission.
spontaneous emission.
Second figure is
Second
showing
figure
the
is
trap
showing the
assisted
trap assisted
recombination.
recombination.
C figure is
C figure is
representing
representing the
absorption
absorption,
and D figure
and D
is
figure is representing the
stimulated.
stimulated emission.
So this was the
So
first
this was
question
the
that
first
we have to
question that we have
identify
to
this
identify the
correct
correct
schematic.
schematic.
So the option
So the
A is the
option
correct
A is the
answer.
correct answer.
Next is asking
Next is asking the
spontaneous emission
spontaneous emission
process in an atom.
process in an atom is governed
So
by. So we saw that
there are
there are Einstein
isotopes.
coefficients.
for absorb.
For absorption,
It was
it
proportional
was proportional to n
one to
1 to
B
b
one to
1 2 and
V.
rho v.
So B1
So b12 is
Einstein coefficient
Einstein coefficient
for absorption.
for absorption.
For
For
spontaneous,
spontaneous emission,
the transition
the transition
from the
is
excited
from the
state to the
excited
second
state to
level
the
to the
second
first.
level to the first level. S- s-
N1.
N1, okay.
So N
So N2
A2.
A21,
Okay. So the
okay.
correct
So the
answer
correct
is
answer is
A2.
A21.
The next is
The next is the
the emission
stimulated emission
process. So
process. Okay, so
the last one
the
is
last one is
stimulated emission.
stimulated emission.
That was given
That was given by N2
B21
B21
and
and rho.
okay.
Okay,
The Einstein
so the Einstein coefficient
for the
for the
stimulated
stimulated emission
in an atom is
in an
given by
atom is
B.
governed by B21.
So the next
So the next is
the radiative
the radiative
the radiative
the radiative
lifetime
lifetime of an atom in an excited
two
state
is
2
given by
is
tau
given by
2
tau
into 10 to
2
the
into 10
minus
raised
9
to
seconds.
minus 9 seconds.
The time in which
The time in which
carrier
the carrier density in the excited
density
state reduces to
1 by E
1 by
times
e
the
times the
initial value.
initial value.
So
So
tau is
tau is
2
2
times
into 10 raised to power
9
minus
second
9 second,
and
and
the formula
the formula for
carrier density
carrier density at time t
is equals
is
to
equals to
n naught
n naught
exponential
exponential
t by
minus
2.
t by 2.
It's asking 1
It's
by E.
asking 1 by e.
Know that
So we know that
it will
it
become
will become
1 by
1 by e
at t
at
is equals
t
to
is equals
tau.
to tau.
So n
So n
tau
tau
equals
is
to
equals to
n naught.
n naught by e.
So tau is
So
equal
tau
to
is equals to
2 into 10.
2 into 10 is to power minus 9 seconds. Option 4 is the correct answer.
Next is the
Next is the Einstein
for the
coefficient for the
spontaneous
spontaneous
emission
emission.
A21 is
A21 is given by.
so the
So
relation
the relation between A21
is
is,
given by
is given by
1 by
1 by tau.
so that is
So that is
1 by
1 by 2 into 10 is to power minus 9,
which is
which is
so it's 5
so it's
into
5 into 10 is to
5 into
5 into 10 is to power
8
8 second inverse.
5 into 10.
5 into 10 is to power.
Next question
Next question is the rate
equation for
equation
the steam
for the stimulated emission
process
process
is consider
is
an
consider
atom
an atom in an
state
excited state
and is
and is
de-exciting the ground
de-exciting to the
state
ground
1 and
state 1 n2 and n1 are the carrier concentration.
so here
So here
1
n1
here and
here n2
excited.
in the excited and ground state respectively.
So we know that
So we know that
a rate of
a rate of change of
population
population
in level
in level 2 is
dn2
dn2 by dt,
and
and it
is
is
proportional
proportional to
n to
n2
UV
UV
is equal.
is equals to,
Since the
since
population
the population is decreasing,
we are
so
considering
we are considering negative sign.
so this is the
So this is the Einstein coefficient.
okay.
Okay.
So the
So
answer
the answer for this rate equation for stimulated dynamic, it will be,
is
because
it's
it's
de-exciting from
de-exciting from
excited state,
excited state to ground state.
so it will depend
So it will depend upon how many
electrons are there in
electrons are there in the
excited state.
excited state.
So dn2 by
So dN2 by dt is equals
minus
to
b2
minus B21 N2 U,
density.
density of states.
Next question.
Next question is,
So we
so
are given
we are
structure A,
given
structure
structure
B,
A, structure
structure
B,
C.
structure C.
So referring to
So
structure
referring
A,
to
which of the
structure A, which
following
of the
statement
following
is correct?
statement is correct?
The band gap
So
of
band gap of
gallium arsenide
gallium
higher
arsenide
than
is
the band
higher than the band
of
gap of
aluminium gallium
aluminium
arsenide.
gallium arsenide.
Band gap of
Band
gallium
gap of
arsenide
gallium arsenide is smaller than the band gap of
L gas.
L gas.
Band gap of
Band gap of gallium arsenide is
GAS gas is
GAS
equal
gas
to the
is
band gap
equal
of
to the band gap of L gas,
and
and so
refractive
and
index of
refractive
gallium
index of
arsenide is
gallium
higher
arsenide
than
is
that of
higher
L
than
gas.
that of L gas
If Ri
if Ri is
smaller or
smaller or equivalent. Okay.
so
So
gallium arsenide
gallium arsenide,
there is shown
there is
the
shown with the,
so
so
suppose this is the
suppose this is
conduction
the conduction
band and this is
band
the
and this is the
you
valence
can
band. So
see
we
that
can
the
see that the
for
whole
GA
GAS layer,
lower
lower
conduction
conduction band edge,
and the higher
and the higher
valence
valence
band edge.
band
Okay.
edge. Okay.
So what does this
So what does this mean
as compared
as
to
compared to,
we can see
we can see
here this is
here this is lower, this is higher. So this is
higher band gap
higher band gap, but this is
comparative.
comparatively low.
So
So
band gap
band gap
in
in
is smaller
is smaller
band gap of
band gap of
this.
yes.
And
And
this is the
so
correct.
this is the correct
Next,
answer.
we
Next,
want to
we want to
comment on
comment on
reflective index.
refractive index.
So in case of
So in case of
refractive index,
refractive
we saw
index,
that
we saw that
smaller band
smaller band gap,
I'm representing
I'm representing is at easy,
implies higher
implies higher
refractive index.
refractive index.
Okay. So the
Okay.
refractive
So the
index
refractive
will be
index
here.
will be higher and the
This.
band gap is smaller.
Next is
Next is,
structure
which
we prefer
structure will you prefer for
fabricating
fabricating
a gallium
a
arsenide.
gallium arsenide laser, and why?
So
So
for a good
for a good,
we just
so we
revise that
just revise that
for a good
for a good semiconductor laser,
we need two
we need
things.
two
First
things.
is
First is
careers
careers
confinement,
confinement,
that is
that is
electrons,
electrons and holes,
and the other
and
is
the other is
optical confinement.
Optical confinement.
That is
That is
guided optical.
guided optical modes.
So this
So
need.
this need.
So what
So
do we want?
what do we want?
These for
These
these two
for these two
characteristics.
characteristics.
This requires
This
that
requires
our
that
active
our
material
active material
to have
to have
smaller band
smaller band gap
and higher
and higher
effectiveness
refractive
as
index
compared to
as
the
compared to
surrounding.
the surrounding.
So for structure
So for
A,
structure A,
for structure
for structure A,
A, gallium arsenide
gallium arsenide is the active material.
it's a
It's a
sandwich
sandwiched
between.
between.
So this
Cladding.
has
So
a
this has
standard.
a
This
standard.
is
This
satisfying
is
both the
satisfying both the condition
career
that
confinement
carriers
as
confinement
well as
as
optical
well as
confinement
optical
because it has
confinement because it has
smaller band
smaller band gap than the
higher
surrounding and higher refractive
refractive
index
surrounding.
than the surrounding.
But
But
structure B
structure B
doesn't
doesn't
have
have
gallium arsenide
gallium arsenide
as the core
as a core
that can
that
confine
can confine
electron
electron
carriers
carriers
and photon.
and photon. Okay,
And the structure
and
C
the
has
structure
no
C has no
heterostructure.
heterostructure.
No
No
heterostructure.
heterostructure, so no confinement.
So
So
structure
structure
A,
A,
since it
since
confines
it
both
confines
electrons
both
and photons,
electrons and
being
photons, being a double heterostructure.
the active region
The
of a
active
diode
region of
laser
a
is
diode
defined.
laser is defined.
So the active
So the
region.
active region,
What is the active
what is
region?
the active region?
Active region
Active region
is the part where
is the part where
injected
injected
carriers,
carriers,
injected carriers,
injected carriers,
that is
that is
electrons and
electrons
holes,
and holes,
recombine
recombine
relative
relatively
to produce
to
photon.
produce photons.
To produce
To
photon,
produce
which will
photons, which will
contribute
contribute to
stimulated
stimulated emission
and optic,
and optical gain,
where
where
it combines.
carriers combined, contributing the useful gain.
So this is the kind.
So
What
this
are
is
the
the
other
kind. What are
options?
the other
Where
options? Reason where
photons are
incoming
absorbed,
photons
so
are
we don't
absorbed,
want
so we don't want
absorption. Okay?
absorption. Okay,
And reason of the
and
double
reason of the
structure,
double structure
heterostructure with lower
heterostructure with lower
lower refractive.
lower
So
refractive. So
we don't want
we
lower
don't want
refractive
lower
index
refractive
because we
index
want the
because we
optical
want the
confinement
optical
also, which
confinement
need
also,
higher
which need higher
refractive index.
refractive index,
And
and
we also don't
we
need
also don't need
band gap,
higher band gap.
lower
We
band
want
gap.
lower band gap,
And
and
reason where
reason where
relativity depends
career depend
non-relativity.
non-relatively.
So
So
we
we
want to avoid
want to avoid the
non-relativity because they don't
non-radiative because
generate
they
the
don't
photons.
generate the
Energy
photons.
is
Energy is
dissipated in some other
dissipated in
form.
some other form of energy.
So the correct
So
answer
the
is
correct answer is option B.
the next is the
The next
essential
is the
features of
essential
marriage
figures
to
of marriage
evaluate
to
the
evaluate
performance
the
of a
performance of a tunable
metasurface,
metasurface, a
bandwidth, modulation
bandwidth,
strength,
modulation strength,
heat
heat
conductivity
conductivity
of
of
the
the
material,
material,
speed,
modulation
and the size
speed,
of the
and the size of the
metasurface.
metasurface.
So we just
So we
by this
just by that
modulation strength
modulation strength
determines how
determines how much optical
how much
How
optical
much optical response
can be changed.
can be changed?
So first is
So first is
bandwidth.
bandwidth. Bandwidth doesn't
Bandwidth is not
Bandwidth is not the measure
the
to evaluate
performance
the
of the tunable.
performance of a tunable metasurface.
It is
It is
modulation
modulation depth because
can be changed.
can be changed. That is
Phase constant
phase constant
delta.
delta phi.
Similarly,
Similarly, amplitude contrast.
the then
Then heat
conductivity. No, this is
conductivity.
not
No,
a
this is not a
parameter. Then
parameter.
modulation,
Then modulation speed. Yes,
like how
like
fast
how fast
how fast
how
device
fast device can
operate. That is,
operate. That is a switching time.
and the size of
And the size of the panel. So
these two,
these
modulation
two,
strength and
modulation
modulation
strength and the
speed, are
modulation
the
speed, are the
fundamental
fundamental
figure of math.
figure of merits to evaluate the performance of a tunable metasurface.
Next is the primary
Next is the primary
for achieving
mechanism for
dynamic
achieving dynamic
permittivity
permittivity
in
modulation
indium tin
using
oxide.
indium tin oxide.
So
So
in
in
ITO,
ITO
is a
is a
first of all it's a
first of all it's a
transparent
transparent conducting
oxide,
oxide
and it's a
and it's a
tunable material.
tunable
So where
material. So where
the
the tunable
tunability comes.
tunability comes. So
Tunability comes
tunability comes from
electrostatic
electrostatic
accumulation.
accumulation
Or
or
depletion
depletion
of
of
carriers
carriers
at the end.
at the interface.
So
So,
we can
like we
apply
can
if we are
apply if
applying
we
a
are
voltage
applying a voltage
bias,
bias,
applying a voltage
applying a
bias
voltage
will
bias
modulate
will modulate
the free
the free
carrier current,
carrier concentration,
which directly
which directly will change the permittivity via Drude model. So,
epsilon
epsilon omega is
equals
equals to epsilon infinity
minus omega
minus omega p square upon omega naught square plus at
common.
gamma omega.
So ITO
So ITO is not a phase change material, so no
amorphous to
amorphous
crystalline
to
transition.
crystalline transition.
So
So
what is the
so
primary
what is the primary
mechanism?
mechanism?
Because of
Because of
injection of
injection
carriers
of
at the
carriers at the
interface due to
interface due
applied
to
voltage
applied
base. Option
voltage
4
base.
is the
Option
correct
4 is the
answer.
correct
So
answer. So
there is no
there is no
there is no
transition
transition
from
from
amorphous
amorphous
to
to crystalline
crystalline
because it's not a phase
because
changing
not a phase
material.
changing material.
It's just the
It's just the
electrostatic
electrostatic
accumulation of carriers.
accumulation of carriers.
No magnetic
No
field
magnetic field
and no
and no
physical expansion
physical
and
expansion and
compression.
compression.
The application
The
of external
application of external
stimuli.
stimuli.
The last question is
Last
some of
question
the
is some of
prominent
the
permittivity unique
permittivity unique
mechanisms are used
mechanisms
in
are
phase
used
change
in phase
materials,
change
mechanical
materials,
actuation,
mechanical actuation, and
Carrier's
Fourier's
excitation.
excitation.
The correct
The
order of
correct
switching
order of
spaces. So
switching
we have
spaces.
seen
So we
that
have seen that
there are
there
various
are
types of
various types
tunability
of
materials.
tunability
Some
materials. Some
materials
materials can be tuned by
phase,
changing the phase.
some is by
Some is by
mecha- uh,
like
we are
we are
by fabricating
by
the meta
fabricating the
surfaces
meta
on the
surfaces on
elastic
the
substrate.
elastic
So by
substrate. So
stretching
by
and
stretching and
shrinking, we
shrinking,
can
we
mechanically
can
modulate the
mechanically
gap
modulate the gap and hence
mobility and
mobility and then
confinement and
confinement and
photocarrier excitation.
photocarrier excitation.
So switching
Switching
like for phase
like for
changing
phase changing
materials,
materials,
For phase
For
changing
phase changing
materials, the
materials,
switching
the
speed
switching
is
speed is
goes to from
goes to from
nanoseconds to
nanoseconds to
microseconds.
microseconds.
And mechanical
And
actuation.
mechanical
So
actuation.
in this
So in this
movement of
movement of
membranes,
membrane, so
speed ranges
speed ranges
microseconds to
microseconds to
milliseconds.
milliseconds.
And for
And for
photocarrier,
photocarrier
that
excitation, that
is
is
injection.
carrier injection.
So we
So
generate
we generate
what is this?
what does this?
We generate
We generate optically
generate
generate
carriers
carriers
in
in
semiconductor. We are
semiconductor. Like
incident
we are
a
incidenting
photon
a photon and
generating
generating
carriers in
carriers in
semiconductors.
semiconductors.
So for
So
that the
for that, the
ranges
speed
from
ranges from
femtoseconds to
femtoseconds to
picoseconds.
picoseconds.
So the
So
correct
the
answer
correct order of switching is
PCM is very
PCM is very nice. No,
PES.
PE. Yes, so
PE,
PE,
then
then
PCM,
PCM,
and then P.
and then PA.
So P this,
So P
this,
this,
this.
this,
So the
this. No. So the
correct order is
correct order is
the phase change,
the phase
the
change is
mechanical
the mechanical actuation, the change in
movement of membrane
movement of membrane
take a lot of
take a
time.
lot of time.
After that,
After that, phase
change from
change
crystal
from
to
crystal
amorphous
into
change
amorphous
time
change time
takes time,
takes time,
and the lesser time
and the lesser time is taken by
in optical
in
generation.
optically
So
generating
the
carriers.
correct
So the
answer is
correct answer is
option B.
option B.
Okay.
Okay.
So this was the
So this was the
assignment 7.
assignment 7,
Today we
and
talked
today we
about
talked
how
about
can we
how
tune
can
the
we tune the
metamaterials,
metamaterials,
what are the
what are the
glazing action,
glazing
what are the
action, what are the
principles of glazing,
principles of glazing,
what are the Einstein
what are the
coefficient
Einstein
for
coefficient
absorption,
for absorption,
spontaneous emission,
spontaneous
and
emission,
stimulated
and
emissions.
stimulated emissions.
Then why do we
Then
need
why do
the
we need the
miniaturization
miniaturization
of lasers?
of
How
lasers?
can
How can we
obtain it
obtain it
in
in
real systems?
real systems?
And then how
And
is the
then
physics
how is the
involved
physics
from
involved
Hermitian
from
to
Hermitian to
non-Hermitian? How
non-Hermitian?
like
How like
losses we saw
losses
that
we
losses
saw
not
that loss
always
is not
harmful.
always harmful.
By balancing
By
gain and
balancing
loss,
gain and loss,
we can
we can
we can get the
we can get the
non-trivial
non-trivial
applications.
applications.
So
So
this was all
this
about
was all about today.
see you on the
See
next
you on the
Saturday.
next Saturday.
Thank
Okay.
you.
Thank you.